Hello and welcome back to Calculus 3, section 11.2, vectors in 3D. So we are going to upgrade from 2D to 3D by simply adding another component inside the vector. We're also going to talk about IJK notation, and we are going to keep all of the properties we covered in a previous section. So one thing that is missing in the online lecture, the video, are these properties which I added earlier. These are the 10 properties that work for any dimension vectors, and I just gave some quick examples and a quick proof for, let's say, number 6, done in 2D, and then the way to extend that into 3D and just do it completed, right? So now we're moving our vectors to 3D. So we are moving from two-dimensional plane, which was x and y, into a three-dimensional space, x, y, z. Generally, we draw that space this way. Oops, x, y, and z, assuming that there is 90 degrees over here, 90 degrees over here, and 90 degrees over here. Between any two axes is going to be 90 degrees. You can observe this particular system in any corner of this classroom, or at any edge of the desk, or if you have an eraser on your desk, you can look at the corner of the eraser. You can't do it on a bottle because the bottle is around, right? So this is one way to denote the three-dimensional space. Now, it's important to know that these axes actually go past these points, right? Like that. But as you can see, it just makes the coordinate system really crowded. So we actually don't put those. We just use this. This is called the first octet, and I'll explain the octets. But before I explain that, I just want to show another way to represent this would be put x and y axis intersect this way, say, I don't know, 30 degrees in between, and then have the z-axis push straight through. This actually shows both positive and negative x-axis, positive and negative y, and positive and negative z, which is more detailed than the one on the left. Now, disadvantage here is that none of the angles are 90 degrees, where in this case at least this one was, right? So it's technically pick your poison. We will use both of these representations as we go through the class. Because certain images and graphics and so on will be easier to see and observe in one than the other, and vice versa. So we'll use both of these representations. Now, I talked already about an octet. You know the story of quadrants. When you have a two-dimensional flat space, doesn't have to be flat, you draw xy axis, and that will divide that 2D space into 4 regions, and each one of those regions is called a quadrant, and you have quadrant 1, 2, 3, 4 going counterclockwise. Now, for 3D space, we don't get to cut with lines, we get to cut with planes. So you should think of the separation of rooms using walls, where wall would be a plane that cuts through the space, dividing the space into 2 regions. Now, if you observe here, you can create a YZ wall, and you have the XY wall, which would be actually a floor, but the XY floor is actually the ceiling for negative Z. So XY plane is a floor for positive z, but it's a ceiling for negative z. Do we all see that? Mm-hmm. So think of the floor on which you are all sitting now, or sitting chairs, but chairs on the floor. So this floor is your xy plane, and our positive z-axis goes from the floor up. Now the first level, right? This is third. No, we're on the second. Where are we? Second level. Thank you. So we're second level. So the first level is going to be below, and that's where the negative z-axis is. So we have that notion now. We also divide with the wall that goes through x, the wall that goes through y, and I hope that you clearly see that there are 8 spaces that you are boxing. So octets, right? Octo, 8. So 8, say cubes, 8 classrooms or whatever that you can create. Now we can actually do the experiment in here, mental experiment. If I am to, go with the wall through the middle of the classroom, right? And then take another wall and do it this way, we are going to have 4 rooms, right? So if I just put 2 walls, right, at 90 degrees to each other, one go middle way that way, and one go middle way this way, you are going to have 4 rooms in this one room. And then go to the middle height, and then put another wall, which is going to be another, right? So this 10-foot ceiling will actually become 5 feet, and we would have actually 8 classrooms. So we would divide this one classroom into 8 classrooms. So the first octet is the one that we generally work in. The first octet is the one where all of the axes are positive. And then numbering conventions for the rest of it don't matter because we just worry about the first octet. So over here, if you connect in some kind of triangle, you will be actually looking at the first octet. And then over here, also with a triangle like that, you will be looking at the first octet in terms of the space. So this is our coordinate system. Now we are intersecting 3 number lines, number line x, number line y, number line z, for 3 dimensions. They're all intersecting in 90 degrees. And we have basic number lines which contain positive and negative numbers. Since we have 3 lines, 3 degrees of freedom, we will define now a 3-dimensional point to have x, y, and z, so 3 dimensions. The way to graph a 3-dimensional point is to follow and count along the axis that you need. So let's take a look at a problem here. Say graph 2, 4, and 6. Whatever. 2, 4, 6. It's better than 1, 2, 3. I'm bored with 1, 2, 3, so there you go. Okay, so at least 2 of these axes, namely y and z, are quote-unquote normal, right? Normally drawn. So I can show 1, 2, 3, 4, which I need on y-axis, and 1, 2, 3, 4, 5, 6 on z. Yeah, luck. Now, here's 2 on x-axis. Now, if you have issue with drawing things and seeing things, it's time for you to just drop the pencils and just stare at the projector over there. I'm going to start with, let's say, purple for number 2, and I'm going to travel from the origin along x-axis to number 2 and stop, and that's the purple part. Then I'm going to pick up the blue, and I need to go 4 units in y direction, so I will go 4 units in y direction. And I'm just going to draw this construction line here that helps This line is parallel to x-axis. So at the purple point, I am at 2, 0, 0. Now at this blue point, right here, I am at 2, 4, 0. So the blue point is on the x, y plane, is on the floor. So you walked alongside one of the walls, the x wall, and then you went parallel to the y wall, and you got to the point 2, 4 that is on the floor. Could be your location where you sit, all right? 2 feet this way, 4 feet that way. And now what I need to do is to go 6 feet up, right? 6 units up. I will draw the parallel line to z-axis and take this much space and add it to that vertical line to see where the point is. So now with the red, I am going to first use the light red, construction red, to draw the construction line here, which is the vertical line that will help me do this. And now I know that I have to go 6 units up. So I have 1, 2, 3, 4, 5, 6 units up. And this is the red point, which is 2, 4, 6. So you walk along the x to the point you need, then draw the parallel line to y and go 4 units along that line, and then draw the vertical z and go up or down, positive or negative, whatever you need to do for z. So it's possible to locate these points and make sense of them even if we are on a 2D. So this is a 2D representation of a 3D point on a 2D surface. Yes. Yes, many times. And now you see where your weekend goes, right? I know. I'm going to take the ruler, and it's going to take some time, and you'll be just fine. Actually, no, you're not going to have to draw this. There will be lines and planes and shapes and things. This is technically warm-up. This is going to be something that you will draw just like that. I'm going to have more granular things, right, to draw. So there we go. That's the 3D point. Again, 3D, we have 3 systems. Hello, physics. Right-hand rule. Anyone? Yeah, right-hand rule, right? Right? Okay. So observe the motion of my fingers. If I have a z-axis, which is actually represented by my thumb over here, and I want to grab around z-axis, you see my fingers are first going to hit x-axis and then y. Because x-axis is going this way, y-axis is going that way, so I pass through x to get to y to wrap around, and here is the positive z, the OK, going up. So if this is a z-axis that exists in the world, I come in, I go through x to wrap around y, because that's the motion my fingers are taking, go through x to get to y. It's called the right-hand rule, right? It's the right hand, it goes x first, y second. There is a left-hand rule as well, where these guys swap locations. That will be y, that will be x. And certain engineering will use that, and you have to be very careful, right? Because in that case, left is right and right is left. So, yeah, mechanical engineers have lots and lots of fun, right? You have those options to switch that in your AutoCAD when you do it, so pay attention, right, to those kind of things. I had a professor that gave us a trick question. It was awesome, right? Gave us a paper. No one looked at the corner. The little thing had x and y swap. No one could get the problem on the test. It was really frustrating. No questions. I know. Just, what happened?
You got it right.
No. Hey, pay attention. You never forget things you get wrong. I still remember my trick question that I got wrong. Tangent x equal tangent cube x. That was the equation I had to solve. I got it wrong. I didn't get it wrong, I got it incomplete. It was really annoying. It's 98 on the test.
Incomplete is wrong.
It's not 100. What happened? Yes. Right. See you next week. I know. Oh, perfect. And here's the, the picture in the book of the thing that I was explaining 35 minutes. Right? So you can clearly see on this picture 8 rooms, right? There are 4 rooms above the blue plane, which is the floor, and 4 below the blue plane, which in case is ceiling for those below. And the blue plane is the XY axis. Now, guys, the blue plane is exactly the plane that you are used to from Calc 2, Calc 1, PreCalcs, and so on. That is that XY plane, which we now take from the board when I draw the XY plane on the board, right? And put your parabola here. Technically, what I'm doing now in Calc 3 is I'm ripping this board off of the wall and I'm just placing it on the floor. That parabola y equal x squared is still on that xy, and I can actually, as you can see, I can walk on that parabola. Right? I can go back on the same parabola where I was. So there is that parabolic shape. I can have a trig sine function, cosine function, I can have anything. So the good old xy plane is included in your new 3D system, and it's just a 2D thing that you can draw with a chalk on the floor. Take a little bit of paint, right, or whatever, and you have your xy plane on the bottom. And now we are introducing the z axis, which gives us the 3rd dimension. Good. Oh, and another graphic. These coordinates are also known as the rectangular coordinates. Here's your 2, 4, 6, the blue, red, and green. In this ABC over here is 2, 4, 6 in a textbook. You can see that this point traced, and you're able to construct the rectangular prism, right? So in a 2D XY world, when you put a point, the only thing you can get there is the rectangle. Now, this is a 3D rectangle called rectangular prism. So we call these coordinates rectangular coordinates. So rectangular coordinates 2D, rectangular coordinates 3D. We have polar coordinates 2D, and then we're going to have cylindrical and spherical upgrades for 3D later on. So there are these are all upgrades. We're not learning anything from scratch. We just need to find where the old stuff stops and where the new stuff builds up. To keep with new. All right, what else do we need to talk about? So we know how to find the point, and now it's time to talk about planes. Okay. So you know the point is one of the fundamental structures, right, that we points are locations in space. The dimension of a point tells you the type of the space that you're working in. So if you have a 2D point, it's a 2D coordinate system. 3D point is going to be point floating in space somewhere over here. Now, the next thing up would be a line, which is the major thing to divide with in 2D. So anytime you draw a line, infinite line, you divide all of the space of 2D into 2 spaces. Each one of those spaces is still infinite. You can't say you divide it in half, no matter when you draw the line. But the fact is that you are splitting the 2D space with the line in two regions. So just draw a line through 2D. It's clear that it does that. You cannot do that with a line in 3D. But you can with a plane. Plane is going to cut through the space, and every time I say plane, the first thing you should think of is a wall. There is a wall over here that you can all see, and this wall separates the space of the hallway and the classroom. So the main mean of division in a 3D space is a plane, not a line. We do have 3D lines. We are going to find the tangent lines. We are going to find straight lines in space. We are going to use them in parametric form and all of that kind of stuff. We're all going to do that, right? 3D lines exist. They intersect and they're parallel and everything else. But they are not fundamental division unit because they do not divide space. They divide space in 2D but not in 3D. In 3D is the plane. So now we want to understand the main units of division, which is the plane. For 2D, your main division lines were x-axis and y-axis, where x equals 0, y equals 0 are each of the axes, and those would cut, right, the space. But you also had a vertical line, let's say x equals 2, right, which cuts the space to the left and to the right of 2. Now, you are going to set the plane through x equals 2, y equals 2, z equals 2. And those planes will divide the space. Now, plane divides everything, and equation of the plane, which we are going to cover, obviously, a little bit later, is going to have all these kind of bells and whistles. But the most basic plane is to say, let's say z equals 0. Maybe we want to start right there. Plane z equals 0 is the floor on which you are walking. All right? I told you that if you ever get stuck in space of what's going on in a problem, you always can fall onto things that I can't take away. And that's the floor. That's your xy plane. And that is actually z equals 0. So we start by understanding the basic equations of the plane. And we start with, I'm going to use the isometric view over here. So these x and the y here would create a plane whose equation is z equals to 0. I am going to put in a parenthesis floor. So z equals 0 is elevation on which this plane is on. I will one more time remind you that even for horizontal asymptotes in 2D, you had the line y equals 0, which went through 0 on y, because this is where the 1 and 2 and negative 1 are, right? So line y equals 0 is x-axis, but it's y equals 0 because it's on elevation y. Y measures it. And then, if you want to have another line at 3 feet, that line will be called y equals 3. So now, as you can see, equation for a line y equals 3 is a horizontal line, and that equation doesn't contain any x in it, because x takes on all of the values, from negative infinity to positive infinity. Pick any point along this horizontal line, and you will always find that you have whatever x is there, comma 3. So y is pinned to be 3 at all times forever. And that's why the equation is y equals to 3, and it doesn't matter what x is because it takes on all of the values from negative infinity to positive infinity. Move to now your 3D case. Floor. Floor is going to go through the origin where z is equal 0 elevation. What's the ceiling? It's 10 feet.
So
Z equals 10. So if I want to describe this classroom using the measurements we are currently learning in terms of planes, and I set up my origin to be in the on the floor in the corner over there, the floor is explained by z equals 0. The ceiling is explained as z equals 10. That wall, the white wall, I should have actually used that corner over there, but then because we have a green wall, but whatever. So this wall here, where we have the door, is going to be, say, x equals 0. If that's x equals 0, the wall parallel to it is x equals whatever amount of feet. We have, how many feet do we have? Exactly, please? Exactly.
from this wall to there?
Yes. You're sitting in Calc 3, I want to know exact.
Let's say 50.
No, exact. He's going to give me exact. 34? 33? Okay. 34, fine. So, 33 or 34? How do we know that? Tiles. I know, each one is 2.
What about
But they're partial tiles.
Yeah, you got partial.
That's okay, we'll deal with that.
That's not exact.
I took that into account.
It's fine. So, you want to be engineers? Start observing stuff. I'm sorry. Wake up. It's Calc 3. The hell? So, each one of these ceiling tiles is 2 feet wide. Count the number of tiles times 2 and then let a little bit there. So what do we have? Our floor is z equals 0. Its elevation 0 because the z-axis goes up. That wall, if this is my x-axis, right? My x-axis goes this way. That's where the 0 is. This way. Past the point in the wall is negative infinity on x. But this is positive x-axis going this way. So that's a 0, x equals 0 wall. And that wall over there is x equals 34 and the for the little part over there. So that's x equals 34. This puppy here is y equals 0 because that's the y-axis over there. So if that's the y-axis, then this is y equals 0. And now you go, okay, that's 4 times number of tiles. You know exactly the equation of the other wall. And now you have enclosed this space in a box using mathematical equations. Hello, mechanical engineers? Anyone? No? No mechanical engineers? So cool. And that's how you make your money. That's where it starts. Yes?
How would we know which one is X and which one is Y?
Depends on the way you set up your coordinate system. Is it the right hand? Is it the left? Yes. Positive z is going to go up because negative z is gravity pulls towards the center of the earth, right? Move away into the middle of the space, you have to make your own, right? So, this is, yeah, this would have to be x for the right hand system, yeah. For the right hand system, this needs to be x, which means x equals 0, and x equals whatever the hell we said, 34. That's the y-axis, right? Remember, guys, right hand rule, positive z. Here's your z-axis. This green thing over here is your z-axis. I come in, I go through x first towards y. So x first, and then y. Z goes up. So now I have x-axis. If that's x-axis, this wall must be x equals 0. And then you walk 34 feet on x to that corner. And now this wall which is perpendicular to x-axis and parallel to the x equals 0 over there, x equals 34 is this wall here. Y equals 0, y equals 30, whatever, over there. And then z 0, z is 10. Are we agreeing on that? Now you know what you're going to do when you get home, before you pass out tonight. You're going to do the same exercise before you pass out in your room. Because you have to. It's now a new frame of operation. You haven't done stuff in 3D, and you have to start thinking about it. So to make this graphic more pleasant, instead of my chicken scratch, ta-da! There's your floor, there's your ceiling for Z. Here are your parallel planes for Y and parallel planes for X's. And as you can see, we only have X equals a number, Y equals a number, and Z equals a number. As soon as you include any addition or subtraction of any two of these, you start getting slanted planes. So let's talk about the slope of the roof. Let's talk about the slope of the driveway. Let's talk about slope of the pavement in terms of, for water to run off during the rain. You can't just go and just put a flat concrete spot, right? It's just going to retain all the water. Same thing, the road construction. Do we have any civil engineers, right? You want to be constructing roads and bridges and stuff? You better make them parabolic a little bit, right? Because if you make them wrong way, you're just making a lake for everyone to drive in. Technically, if the roads are constructed properly, the best lane to drive in during the heavy rain is the middle lane, because all of the water should be running off, and that lane should be technically the driest, right? I mean, the smallest amount of water. You have the rain incoming everywhere, but the runoff, because the parabolic shape of the road, should be that way. So there are a lot of things, guys, and all of this is very relevant for that stuff. All right, so I will draw this, but I just wanted to make sure. Now, if you observe my drawing here, it's terrible because my blue lines are not parallel to the black lines, which are axes. So, when something is terrible, you do it again. So, to draw this plane, I'm going to draw two parallel lines to x-axis and two parallel lines to y-axis, and all of a sudden you see that this is much better drawing than before. So figuring out where these parallel lines should go will give you much better representation of what you're trying to draw. Now, if I need another plane to say we are going to go higher, I still have to do the parallel lines. But see, now I can do this. And obviously, with some practice, it will start looking good. I'm going to label over here the green dot and say, let's say 4, which would make this one z equals to 4, and that's going to be my ceiling. It's possible to draw these things. You just need to, you need to practice a little bit. Or a lot. So once we have a floor and a ceiling, which in my opinion are the easiest ones to digest because such is life, I guess, we can go and discuss the x and the y planes. And let's see if I can do a good job over here. So we have our x and y, and now I want x equals 0. Now, clearly, for x equals 0, I need parallel lines to Z. If you haven't noticed before, when I talked about Z, all of my parallel lines were X and Y to create a plane. So I use the ones that are not Z. So now I have to use the ones that are not X, which means Y and Z. So parallel lines with Y and Z will do the trick to draw the plane that it's X equals 0. I'm going to extend the negative Z axis, and to actually make this better, I'm going to erase the extra lines and just keep the plane, which would be easier now to see that this plane is actually X equal to 0. Now let's say we want to construct another one at X equals negative blah, right? So the way I'm going to do that is, again, set up two parallel lines that represent my Z, and then parallel lines for Y, and then erase the extra. I'm sorry if you took computer graphics and now all of a sudden this is too boring for you, but this exercise is not just, to show off how well you can do in doing this by hand, but also reading technical drawings, guys, especially the 3D assembly ones. I mean, you have to have that skill. And practicing these, especially you guys, and civil engineers and so on. And electrical is a little bit different. So you have to be able to read and make sense of all of these things. Now, as a challenge to all of you, before I draw anything, Y equals 0. Get busy. Please make sure you bully people around to get their drawings straight.
You can't really humanly do it well. So what I did is I tried to push this goal kind of behind, and then I said, just put it in 2 or in 1 or in whatever. Hopefully you see that the blue one is behind the green. Okay. So I could have moved through this kind of.
And then X equals 0 in front.
X equals 0 is in front and goes to the. Maybe I should.
No, I was just trying to know.
Well, it's fine. It takes time to get used to this stuff. Your assignment is to draw Y equals 0 and then Y equals 3 or whatever. So 2 parallel. First rule of engineering, draw big. If you have to squint to see anything, you're doing it wrong.
It has to be, so if X equals 0 is negative, to X and Y, or X. It's actually infinitely better.
Only just now can do that.
You remember the rhythm from our last class. not my home. It's part of homework, so I haven't done anything other than copy the course. Copy in my network is already done. Talk about zero and zero. Took the very simple concept, plug in my project and my monotonous exam on the policy and the class. Okay,
thank you.
On 6 or 7 pages.
And that would be for the one.
And then for your homework, I haven't even set the thing. The cost of the thing is it was for the last semester. There you go.
Setting y equals 0 and y equals
Setting on half of the homework.
So for y equals 0, center it there. Then you want x equals -3, right?
So how is this line parallel to z? Can you explain that to me?
It's not.
It's not, exactly.
So I have to draw that part.
Remember, y equals 0, you have to have stuff parallel to z's
To z.
and to x's.
To x's.
Yes.
Okay.
So z's and x's have to be parallel.
Alright.
All right. As I walked around, I looked briefly at some of the work, and we have the mixed bag of things, right? Going from the back to the front over here. We want to draw y equals 0, which means that our lines will have to be parallel to x and parallel to z. We will set again the isometric view over here, x, y, z. I missed that one, right? Oh, come on. In order to draw y equal to 0, I'm going to draw parallel to x and parallel to z. So parallel to x, and let's say over here parallel to z. And then erase the extra. And yes.
Can you just repeat, so for y equals 0, you always do parallel to x and z, right? Always for the one.
Let's not do it that way. Let's do it in two-dimensional space. If I want y equals to 3, it's parallel to x-axis, right?
Yeah.
So you can think of it that in those terms, because if you clearly have an issue with the way I am explaining, switch to whatever other thing is out there available, which would be that thing.
Okay.
And if we want to go to, say, y equals to 3, right, the other plane will be in front. So this is y equal to 3, and the green one is y equal to 0. It will be highly beneficial for you guys to do the exercise before you pass out tonight if you know the dimensions. If not, just take a little box of something, measure the box in terms of inches, and then figure out the dimensions of that box. Now, as we go on and do the slanted planes, as you can see, this is not a box that has the vertical sides like our classroom that has walls that are perfectly right. This is more of a, if you cut it, it's a trapezoid. So these guys on the edges here are not going to be x equals y equals kind of line. There are going to be some combinations of x plus y and x minus y and so on that it also involves the slope. And you will still have your z equals 0 and z equals, what is this, 2 inches, 3 inches, right? So z equals 3, z equals 0. But then these guys are going to be a little bit more challenging. This makes it for a nice little project, right? Describe the shape in terms of planes. So what planes do you need to intersect? And you need to have 6 planes because there are 6 sides. If you say this is closed and this is your z equals 0 floor, right? When you put it on the floor, there you go. You want something to really think about once we cover the rest, because you can measure exact coordinates in space for each one of these points and then set the planes through those points. And we are going to learn that we need 3 points to set up the plane and so on. It's a nice little project. Then you go ahead and draw it in AutoCAD. Yes?
I was still thinking about earlier how you mentioned, like, for instance, a roof. Would it be easy to just take it in, like, respect to the y and z axis in that case, and just take the differential of that, of y in respect?
Well, it has to be a z-axis because it goes up and down, roof, yes. Right? But then the question is it going to line up with your coordinate system, okay, or it's going to be rotated? So the roof that is this way, if your xz axis goes this way and the house is oriented this way, you see?
Yeah. That's how
there are a lot of headaches that can pop up along the way. Knowing this is very important. Great. So now you know the simplest possible equations for a plane. X equals, y equals, z equals. Those 3 basic equations of the plane will always be enough for you to create a box that has 90 degrees everywhere. And we already seen that we can enclose this classroom with 6 of those equations because we have 6 walls around us. I know that this wall is called a ceiling, so special, right? But we have 6 walls around us, and we can express each one of those walls with these basic equations. Now, I would also like to measure distance in third-dimensional space. We all hopefully know the distance formula in 2D. You will very quickly figure out that extending 2D formulas to 3D formulas is just adding a same term. So, distance in 2D was given by the distance formula square root of x2 minus x1 squared plus y2 minus y1 squared. This was known as Euclidean distance. It represents the straight line in the non-curved flat surface. We call that Euclidean surface. And you clearly are connecting with a straight line x1, y1, and x2, y2. You're connecting these 2 points with a straight line. On the flat surface, the shortest distance between 2 points is a straight line. That is not true for the surface of the planet. And we'll talk about it when we get to that point. So, for the flat surface, for your 2D, the shortest distance between 2 points is a straight line. Your floor, which is your xy plane, in this case, is flat. So the shortest distance to get out of the classroom will be to walk straight towards the door. But if you want to fly from New York to London, you do not want to fly in a straight line because you might not make it because of fuel. We'll talk about that. So now, how do we extend this formula to 3D? We simply are going to copy and paste the formula we have and add the z term in the mix because we know that the 3D points are x, y, z. So now, in red, this is the new material for our Calc 3, is distance in 3D. Distance in 3D, considering points x1, y1, z1, and x2, y2, z2, is going to be given by x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And that is one of our formulas. Oh, we also need to mention right at the beginning, there will be no formula sheets of any kind on any test on any of the things, because the formula sheet will completely destroy Calculus 3. It would literally collapse it to a Calculus 1. You learning Calc 3 means just two things. One is understanding the 3D realm, and two, learning all the formulas that surround it. All of the other calculations and things that we do will be straight Calculus 1 calculation. We are not learning anything new. Partial derivatives will be a little bit obscure, but that's going to be chain rule kind of close to it, and that's it. You will see integration, U sub, and basic integrals and stuff like that. So you absolutely must learn the formulas, keep the bank of the formulas, keep writing them, copying them, and learning them, because this is what Calc 3 is all about, learning these formulas. And I already gave you one of the biggest secrets of Calc 3 formulas. If you know your Calc 2 formula, most likely you're just adding z at the end and you have your Calc 3 formula for it. In the interest of time, we can just skip calculating examples with the point 1, 2, 3 and whatever else to, right? Next one is midpoint. In 2D, what was the midpoint in 2D, anyone? Nice. Average of x's, comma, average of y's. Nice. It's the midpoint. Therefore, the average. So we have average of x's and average of y's. All right. Switching to red. Midpoint in 3D. What's the midpoint in 3D?
Same thing with
add the z into the mix. So just add the average of z's. So average of x's, average of y's, and average of z's. Equation of the sphere. Well, circle in 2D is equivalent to, gives rise to the sphere, which is a ball, in 3D. What is the equation of the circle?
X squared plus y squared.
So now what's the equation of the sphere?
x squared plus y plus z squared.
Pop in that z squared. Now we do not want to restrict the ball to always be in the center of the coordinate system origin 0, 0. We want to make it free to exist anywhere, right? So, sphere, I am not going to put in 3D because there is no sphere in 2D, and then we are not dealing with the fourth dimensional sphere, hypersphere, so it's enough to just say sphere. It's a 3D. The equation is going to be x minus a squared plus y minus b squared plus z minus c squared equals r squared. Center ABC, radius r. Again, I'm going to circle it over here. You are used to HK. Now you have to deal with ABC. Yeah, tough luck, right? So here is your two-dimensional circle equals R. And now if you add Z to the mix, we are changing H and K with ABC. We have the sphere equation. Can anyone in infinite wisdom tell me the equation for hypersphere? Add the W, exactly. W minus D squared. And there you go. You have the equation for hypersphere. You can go to any number of dimensions. If you are using the alphabet over here, right? You go as far as alphabet will allow. How many dimensions would that be? Nope. 13. Nice. Because we have to use A, B, and C, D, E, F, G, right? And then we're going to get X, Y, Z, W, so maybe Q. So go backwards for variables and go forward for the center, 13 and 13, right? For 26 letters. Oh yeah, it has R, you're right. We ruined the R, so it's like 12 and a half dimensions. We can't have that. Yeah, 12 and a half dimensions. Very good. Nice. Okay, great. So we've seen that we can recycle our old equations and just tag along this Z business at the end, and that works for almost anything. We are going to see that we're going to tag along that in integration later on. Our dx integral is going to become dx dy, eventually dx dy dz. And then we can shuffle those in any way, and then maybe have dx dz dy, or dz dy dx, and so on. So we'll shuffle those eventually. And oh, we're supposed to talk about vectors. Here we go. So vectors. So now we know the 3D environment. We understand the basic stuff in a 3D environment. And it's time for vectors in 3D. Now, this notation 3D has a better representation which we use in mathematics. And that is going to be R cubed. So 1D is going to be denoted as R with a double bar, right? Capital R. And the meaning of that is negative infinity to positive infinity. It's all real numbers number line. That's what your 1D is. Now 2D will be denoted as R squared. And now this is a Cartesian product of x dimension infinite line with the y dimension infinite line. And then you have your 3D, which is R3. Your linear algebra will have Rn, going to whatever amount of dimensions you need to go to. So this would be the triple product because you need to have the infinity. These are representations for your x, y, and z axis, which in the domain stretch from negative to positive infinity on each one of the x and the y and the z. So this is the notation. Next time when I say 3D, I will most likely put R cubed, so you all need to know and understand what that means as we go along. Now, the vector in 3D is going to be your good old friend U, but that vector is going to have now 3 coordinates, components to it. So now vector u in 3D is going to have u1, u2, u3. The vector in 3D space is going to connect from the origin to the point u, which is the terminal point, and that is u1, u2, and u3. But the vector u will have the same u1, u2, u3 components with the spiky brackets because it's a vector, right? So to make this clear, having the example over here, if I have a vector and this point is 2, 5, and -1, then the vector u will be 2, 5, and -1. We know that we have to subtract the initial point from terminal point. Well, your initial point is 0, 0, 0 because the vector starts at the origin. So it better be whatever the end point is, but you have to be careful. Over here, I must use parentheses. It's a point. Well, over here, it's a vector, so I have to use the spiky brackets. Make sure you use correct notation because it triggers my allergic reaction to you. All of the properties you studied and learned from your 2D vector carry over to the 3D vector. We are talking about adding, subtracting, scalar multiplication, and 10 properties. The only new thing is the magnitude now is calculated using the distance formula, right? And so magnitude of u is the square root of u1 squared plus u2 squared plus u3 squared. Remember we talked about the direction. There is a way to deal with the direction using directional cosines and stuff like that. For the 3D vectors, we just don't do it, okay? And then we also have that, I'll write it in blood, all of the properties from 2D transfer over, because those properties are actually for n-dimensional vectors. Now, that includes addition, subtraction, scalar multiplication, and 10 properties we discussed at the beginning of the class. Clearly, the annoyance here will be that instead of doing 2 calculations for 2D coordinates, you will be doing 3 calculations because you have 3 coordinates now to worry about. So the magnitude, and finally, I get to define the unit vectors. Unit vector I, it's not an arrow, it's a little hat on top. It's a vector, but we use a different notation because the length of this vector is exactly 1 unit. Whether it's a 1 inch or 1 second or 1 mile or 1 kilogram, I don't care, right? It's a 1 unit. And it's a special if it's 1 unit because it's a unit. and we have a hat as a notation, but it is a vector. And the vector is 1, 0, 0. We have a vector j, which is also a unit vector because length is 1, 0, 1, 0, and vector k, 0, 0, 1, for our ijk vectors. Now, those are the carriers here on your x, y, and z, so they carry direction. This is 1 unit in x, that's I. This one over here is 1 unit in y, which is j. And this one over here is 1 unit in z direction, which is k. Now, this allows us to decompose vectors. Those of you who did linear algebra, you know about bases. These are the bases to describe a vector. So if I have a vector u given as 3, -2, and 6, I can write that alternatively as 3i minus 2j plus 6k. Note that this is more along the side of algebra, the way you used to deal with things like x squared minus 3x plus 8, right? And if you need to add vectors, you would add like terms, because this one technically has I and this one has j, so you will be adding like terms using this notation. Clearly, this is much shorter to write, but the other one has the advantages of understanding, you know, the way to compute things and put things together. And that's it. I hope you're not disappointed. Next class, we are going to cover 2 sections, dot product and cross product. So your class preps 11.3, 11.4. See you all on Monday. It's the other room. And write down your SI classroom for next Wednesday.
It's actually an S245, which is just the next room over.
Next room over.
And
That way.
It's going to be from 4 to 5 p.m., but I'm going to stay till 5:30. So if you guys want to just hang out and have some extra help until class time.
Let me say bye. Bye.